Yeah, I don't know, maybe I don't want to talk too much about myself. Maybe I can give you a little bit of background where I'm scientifically from. So I started out in computer science and maths, and I guess I learned about machine learning during my education now 25 years ago. So that's somewhat scary. Guess I'm getting very old. And I was in Edinburgh at that time. That was pretty nice. So studied there under Chris Williams, who's I think at the time brought out his book on Gaussian processes by Rasmussen and Williams. So I can still remember buying that there. And then I came back to Germany, and I figured out that I wanted to really become better at statistics, because that was like the language that all of the nice papers were written in that I wanted to read. But I didn't feel brave enough to already pursue my PhD. I can remember that I nearly applied in Tübingen, but they only had the PhD program and not the master's in ML. I guess if they would have had a master's program, I probably would have ended up in Tübingen. So went to Dortmund. So they had a MSc in data science. So did that and studied lots of stats, and then did my PhD there at the stats department. Mainly on algorithm selection and algorithm configuration. And during that time, I also met some of the organizers of the AutoML Fall School, which of course didn't exist at that point in time. I guess some of us then created COSIR. So that's a network for configuration and selection of algorithms, and it's obviously very close to AutoML and hyperparameter optimization. And for me, I figured out that I wanted to do more in AutoML during my own PhD, because I really liked I liked theory and maths and so on, but I also like practical work. So I did lots of experiments on platforms like Kaggle and so on competitions, and then I figured out that lots of the performance is actually in HPO. And if that's where the performance gains are, would be nice if we would have a proper, algorithmic foundation how to handle this. Now, anyway, I want to give a tutorial-like fundamental, simple introduction to HPO. I will end Bayesian optimization. I will mainly focus a bit on BO. Can you actually hand me my phone? Because otherwise it will be about 1 hour over time, which should not happen. I have 90 minutes including questions, right? But I started 10 minutes late. So let's see how we handle that. And I would like this to be fairly interactive. So I might ask you things in between. I'm not sure. Usually people hate that. If you want to ask, please do this. Just rudely interrupt me, shout, scream, raise your hand, whatever you want. This is really supposed to be a beginner-friendly session. I'm not sure whether I make that work completely, but if you want to ask something, please, that's your chance now. Please do this, okay? Or at least try to answer everything. I'm not sure whether this is a super good idea that I advertise that so heavily, because I have about 60 slides. I'm not sure how Marius made that work for his presentation. I usually get stuck at 30 to 40. If we don't make it completely to the end, I will not be too unhappy. I'll try to do that. But for me, it's more important that you can ask stuff, okay? So please do this. Okay, so Marius. Okay, I can't. Okay, it's just a little bit slow. So that's the program for today. So I'll talk a little bit about HPO, a little bit about quite a lot about BO. Some details on acquisition functions. Short overview on GPs and random forests in the context of BO. A few slides on noisy Bayesian optimization. Some advanced stuff. So talk a bit about parallelization and HIBO, and I'll show you a glimpse of an empirical meta-analysis. Let's see whether we make it to these three, final chapters. So Marius, already introduced quite a lot. I'll go over this rather, let's say with medium speed. Just interrupt me if some details are unclear, especially also if, terminology is sometimes not clear. This is usually a big problem in machine learning, that we have like 5 different terms for the same thing. Just ask. So this is about hyperparameter optimization. So what are hyperparameters? Hyperparameters are inputs to the learning algorithm. Yeah? Next to the data, there are hyperparameters, and they control the training procedure. And they usually control how empirical risk minimization is being performed. Not necessarily only, but very often they control model complexity. This is why we usually use lambda as a symbol, and I'm going to do this here as well. That's like the common symbol for putting controlling the fit versus complexity trade-off, in regularized risk minimization. But this can also be technical control of the optimizer, I don't know, or the implementation or whatever. It can pretty much be anything, and everybody who has done some practical experiments usually has seen that they can more or less greatly influence generalization performance, also the speed of the optimization procedure. And hyperparameter optimization or tuning, I guess some people also use this a bit synonymously nowadays with AutoML. I'll talk about this a bit later. But that's simply the process of finding a well-performing hyperparameter configuration for a certain learning algorithm. So I'll use some symbols later on. So lambda is an HPC, so hyperparameter configuration, so a vector of control settings that we use, and I is my symbol for learning algorithm. We use I because inducer is a fancy name for a learner. Now, for these hyperparameters, there's usually we have to select some that we want to optimize over, and most of the algorithms actually need bounds. So they need some finite bounds. So the space here I'll just call capital lambda or capital lambda tilde. So tilde would be, I don't know, the bounded subspace of the selected hyperparameters we want to optimize over. As Marius already said, these can be continuous, can be discrete, and they can even be categorical. Now, this is the objective function we now want to optimize. So we have some estimator of the generalization performance, and that depends on the inducer, but that's fixed, the learning algorithm. It depends on some performance metric, rho. It depends on resampling splits. So usually you need something like a training validation split or a cross-validation splitting to fix where you train and where you predict on, right? And the actual variable thing that you want to optimize over, so your decision variables are the hyperparameter settings, right? And this, yes, please.
Why is the resampling split called J?
I needed another symbol.
Not like inducer.
No, I can't give a good reason for that. Yeah. Please.
Does it make a problem any easier or harder if you have the discrete or continuous?
Yes. I have a slide on why is that problem so hard. So maybe we can get back to that in exactly one slide. So, how does this work from a high level perspective? So this is our objective function, and we now have some optimizer running on that. So this optimizer somehow proposes a new hyperparameter configuration. This can also be multiple, but let's keep things simple here. So we will just propose one thing. Somehow we evaluate that through resampling. A feedback value is returned, a performance value. We feed that back into the optimizer, and hopefully the optimizer now does something intelligent with that. Somehow adapts, somehow iteratively. We could even say maybe learns, optimizes this thing, and we iterate. Okay? And our variations are usually stored in an archive, so we just put them into a data table, So all of that depends on the configurations we try out and the performance value we observed. Okay? We have that in a nice little table. And I guess what we now want to figure out is how this optimization loop can be constructed in a reasonable manner. So, am I right to assume that everybody knows basics of ML? Because I'm not introducing that. Is that okay? Who has actually had some formal education optimization? So half of you, maybe, or a third. Okay. Convex optimization? discrete? Okay. So I guess, if you've studied optimization and on the university level, usually figure out there's not a single course on optimization. Well, I do teach one overview course like that in Linux, but optimization is a complex topic, right? So usually there are like 1,000-page books on different sub-variants of optimization. There's, I don't know, linear optimization. You can study that for a full year. There's discrete optimization, there's convex optimization, and so on. What we are doing here is something a bit different. First of all, our optimization problems are usually black box. Okay, so what does that mean? We really don't have a formula available to us, and we very definitely usually don't have gradients. So we have something like this here, and I can give it a symbol, but that doesn't really make it a white box formula, right? So it's not basic arithmetic. A neural network might be very complex and large, but for the whole prediction, or for the prediction formula is a nested arithmetic expression, right? And we can work with that. We can potentially compute derivatives, and we can exploit this structure. This here is more or less a computer program. Actually, more than less. So the main thing we can do with this, there are exceptions, but I guess the general AutoML problem, where we go over pre-processing, where we go over many different ML algorithms simultaneously, is pretty much a program. We can stick some configurations in, we can observe the objective value, but that's it. It's even worse. This evaluation is going to be expensive. So this can range from a few seconds, usually it's a few minutes, to a few hours or even days. If data is super large and the models are very expensive, and that constrains our budget quite a lot. So maybe we can do a few hundred, a few thousand, maybe 10,000, 50,000 evaluations, but that's already pushing it. And if we were in a 10-dimensional space, 1,000 evaluations is pretty much nothing. Further, the evaluation is stochastic, right? So just because we fix some training set and some validation set doesn't make it a completely deterministic problem. Or if you fix a seed, the splits are random and the data is random itself, right? So we are actually interested in optimizing an expected value here, and we just see some stochastic variant of that. There are categorical and dependent hyperparameters. That makes the space, as even if we would have some more white box formula available to us, which we usually don't, there is really no measure of a distance. How do you define gradients on a categorical space? Many optimizers cannot handle just a few of these properties, and in combination, I don't know. There wasn't a lot out there that could properly handle this. Even the near Bayesian optimization can't handle all of these. I might be interested. Do you know some procedures which can partially cope with these things here? Maybe especially this mixed structure. An idea? So if you wouldn't know BO, if you go back, I don't know, 20 years in time, 30 years in time, Random search is great, that usually works on everything, Something that learns a bit more than random search?
Evolutionary algorithms.
Yes, evolutionary algorithms are usually pretty good, because evolutionary algorithms are not a single algorithm, they're like a class, and you have to define crossover and mutation operators, but you can do this in a flexible manner, and you can define that in a way so that they also work with this here. They can be applied to stochastic problems. They definitely can be applied to black box problems. I guess that's what they were made for. They sometimes have a problem with this here. So usually they assume that the budget is way higher than just a few thousand evaluations. Few words on pipelines and AutoML. So what I've until now mainly talked about is optimizing the hyperparameters of a single machine learning algorithm. But machine learning typically, usually nowadays, has several data transformation, pre-processing, or post-processing steps. that you have to do in addition to the Miller-Morlin fit. If these steps are in succession, data flows pretty much through a sequential pipeline. You can see an example here, pretty, common thing. You do some scaling of your inputs. Usually you have to do factor encoding. Maybe you have to do some missing value imputation. So that's also very common for practical data. Maybe you have to down filter your features somehow, because there are too many to handle for the learning algorithm itself. I guess it's debatable whether this is really needed for modern algorithms. Sometimes it still is, but yeah, factor encoding and imputation and so on. This is very common and regular. So each of these things here must usually be embedded in a pipeline. And with pipeline, we mean that it actually has a training and a predict step. And that's very important to ensure or to avoid learning leakage, okay? So you can't do these things on the complete global data set and then just cross-validate your machine learning algorithm. No, there's no raised hands. This is a, mistake that many people have fallen into in the past. This really needs to be embedded into cross-validation. And for that reason, we have to stick processing steps with a training and a predict step in front of our ML algorithm. Which means during the training step, we usually transform the data, but we also learn parameters. And during the application phase, so during the prediction step, we then apply these parameters and usually also transform data. Okay? Does that make sense? So, yeah, I know that you know this, Katharina. I guess I'm asking the other guys. At least you were kind enough to respond. I don't know, maybe a simple example here would be the scaling. Let's say we do some, I guess you all know, zero mean variance 1 scaling, right? So what would be the trained parameters of such a scaling operator? What would you learn during training? What are the parameters you store? Yeah, mean and variance or mean and standard deviation, right? So during training, you compute them from the training data, but you also apply them. During prediction time, you only apply them, but you don't learn them, right? Imagine there's, for example, just a single observation. You don't want to, estimate the variance from that, right? You're just applying it. And also you are not, in a certain sense, you're not even allowed to do this anymore, right? You have to collect all of the information, the variable stuff during training. Okay. Well, I guess the answer is also on the slide. So the bad news is that all of these operators usually also have their own hyperparameters. Okay, that sounds bad. On the other hand, the black box optimization problem really hasn't changed, because we now just draw a box around such a pipeline. It's still a learning algorithm. Yeah, I know, some black box, some magic, some complicated stuff happens on the inside. So our way of dealing with that and optimizing that hasn't really changed. The major thing that has changed for us is that the hyperparameter space is now usually a bit higher dimensional. Yeah? And how much depends on the size and the complexity of this pipeline. And very often also there's more categorical stuff in there. There's more hierarchical stuff in there. So structurally, not a big change, but this here is, has become worse, so to speak. Not structurally, but I guess in terms of size. The other thing we can also do is we can really combine this with algorithm selection. So instead of just having sequential pipelines, we can either have graphs or we can have like meta operators where one operator says, I can do algorithm A, B, C, or D. Yeah, this imputation technique or this ML algorithm. So we usually represent that in software through branching, so where data can flow through edges and paths in a graph. And then you have these, branches where you can say, go left, go right, go middle. Yeah, take this ML algorithm. Yeah, take the random forest, take the support vector machine. Do a neural network, use gradient boosting, do this or that pre-processing. And through hyperparameters, you can now control how data flows in such a graph. Yeah? Or you have, I don't know, onion-like operators where in one operator there are multiple other operators hidden inside of that. Does that also make sense? Yeah.
But this is still a discrete case, right? Like, is there also a way to kind of like encode this in sort of a latent continuous latent space? If you can do like region-based optimization or like deselection?
You can do that. I'm not going to talk about this here. This is potentially possible, but the problem will usually still be black box, right? So you would have to at least usually estimate gradients there. Yeah. And this is how, I don't know, how such a search space might look like. Yeah, I guess we talked about this. I guess I said all of this. So usually, in my opinion, a possible, I don't know, definition of this hyperparameter optimization for AutoML might be some flexible way of writing down such a search space. That means you need a modeling language to express these pipelines. Yeah? And I would say we have seen great progress there in the last 10 years. So you need something like a domain-specific language for such ML pipelines, and then you need a flexible optimizer to configure everything. And I guess it would be quite nice if we have an open system where a human can now write down. I mean, we talked about theory and constraining the search space, right? So you maybe want to come up with your own intuition, your own ideas, which components might be interesting. Yeah? And you've taken this from literature, from previous experiments, but this is not totally carved in stone. And you write down such a space, such a pipeline space, and then you hit that with an efficient black box optimizer, to configure all of the, I don't know, the numbers, the concrete settings, which also might vary a lot from task to task. And that such a combination of such a DSML domain-specific language plus an efficient optimizer, that might be one definition of AutoML. I guess ensembling and things like autogluon is an alternative. Yes.
One question to put that before, like where you showed the diagram. Yeah, exactly. What is defining the y-axis of this diagram?
There is no y-axis. There's x1 and x2. So you mean this here?
No. I'm
sorry.
Like your graph, like the graph you have there, like the factor encoding. Then you go to PCA.
Are we talking about this slide or a different one?
Yeah, this one.
This one.
Like there, you like now this like this structure is even this. Yeah, exactly. This what is telling you the hierarchy of things?
Well, the idea, I mean, this is how we often encode this in software. So what we do is we want to have like a flat structure or a non-nested structure where we don't have operators inside of operators. So the idea is that you have something here like in German it's Weiche. I don't know what this is actually in English. Branch, a forking path, and you now have a hyperparameter which controls whether data flows here, for example, here left or right, or goes here, here, or here. And then the settings of this node would be subordinate to the setting of this one here. Does that make sense?
Yeah, my question was just like if I have, I don't know if I get this correctly. This is like your choice of hyperparameter. This shows your choice of hyperparameter. So, like, in order to sort them in a sequential way such that you can decide, I want to do this, then this, then this. What defines you this? Like, what defines you what comes after?
I do this as a modeler, or you do something like t-put, where you even optimize over the structure. But like defining the potential setup of such a graph, which is pretty much a pipelining space, so to speak. This is what I often do as a modeler. I would like to do this more based on empirical data. This is quite hard. You can, of course, also hit that with black box optimization, but this becomes very difficult. You're pretty much then in, I don't know, the realm of genetic programming. This is very hard to make that efficient. So very often what I do is that I write this down for a certain class of problems because I have some form of intuition. And And I like doing that. What I don't like doing is figuring out what of the stuff really works and figuring out the numerical settings and so on. And in my opinion, I don't know, we have become a little bit too monolithic and black boxy ourselves when these things are not easily changeable by users. Because either the space is too large or too small. Yeah? Very often what you want is some common choices. Yeah? I don't know. If it's tabular data, I guess you want to try out gradient boosting and so on. But very often you want to do some form of custom feature extraction, some custom pre-processing that makes sense for the data at hand. You somehow need to be able to push that into the system, and then certain other things, they don't make any sense, right? Because the models may be too complex, too slow, whatever. Yeah. Okay. Some naive approaches how to do this. I guess we can manually tune this. Yeah, I mean, I guess we are all here because we don't like that too much. It can actually sometimes still lead to good results. So humans are amazingly good at that sometimes. On the other hand, this is very often, it's tedious work. It's inefficient. I guess some people like doing that. I don't. It also is really not reproducible. I guess Marius has talked enough about this. I guess everybody also knows random search and grid search, right? Yeah, so we can, of course, discretize all of our parameters. Well, not sure whether this is so obvious and so easy. And then, try everything out in a cross-product-like way. Or we can uniformly randomly sample from our space and then run some random experiments. This has lots of advantages, right? You can implement that in a few lines of code. Easily parallelizable. Random search is even an anytime algorithm. Yeah, if performance is not good enough, just run it again. Or let it run on. You can have that run independently on 10 different workers. You can even just at the end merge the results. So this is quite nice. Of course, this learns nothing. Yeah, this is completely stupid. Do you have an idea why we usually nowadays try to tap? Marius advertised Bayesian optimization a lot. That will come in a few minutes. But if you at least compare random search and grid search, why do we try to at least get people away from grid search and at least do random search? And sometimes random search is actually not so bad. When we use it as a configurator from ML algorithms. I guess that's two questions. So let's first compare random search and grid search. Is there a really big difference between the two? I mean, Marius talked about the Bischl paper. Yeah.
You're wasting a lot of time on bad configurations.
Yeah, but that's true for both, right? That's not that's not the difference between the two, right?
If you just like do 3 maybe.
It would do like the 3 over there, but this would go like find some space maybe.
Yeah, but I mean, if this region here is bad, I'm spending the same budget on that region here and here, right?
You at least have the chance of a varying sample density. So you can be lucky and find like something you cannot resolve on the right.
That's a bit closer to the truth, I would say. So here, this depends on the discretization, right? So if I'm unlucky, I've constructed this in such a manner that the interesting stuff happens here in between, and for random search, it's not completely ruled out, right? Yeah.
I mean, because random search basically is a Gaussian distribution, and most of the samples from the Gaussian comes. But like most of the samples in a random distribution would be closer to the mean.
But that's actually not what most people do. Most people fix some bounds and then they uniformly randomly sample. If you do Gaussian, you then have to talk about where is the mean, how large is I don't know, the standard deviation, or how's your. I mean, I don't see this too often. I mean, I see this in algorithms, but then usually these are a bit more advanced, and I wouldn't call them random search anymore. There's one other thing you can kind of see or discover, and that's sometimes we have parameters in the space which have no effect. Okay, so that's I guess somewhat educational to think about it like that. So here we have two hyperparameters, right? I don't know, lambda, yes, x1 and x2, lambda 1 and lambda 2. Pretend that x2 doesn't have an effect. Lambda 2 doesn't have an effect. So, and then you do 10 times 10 on your grid. So you have a budget of 100. How many effective evaluations have you done here on the right-hand side for grid search? 10, right? It's pretty much projected on the lambda 1 axis, so to speak. So you have wasted a factor of 10 of your budget for random search. That's still 100, right? Now that's, I guess, one of the reasons all of this anytime stuff and so on, I don't have to think about discretization and so on. These are practical things that also matter and are quite nice. Yeah. Okay, but actually we didn't, I'm not sure whether I should do this too much. Yeah, probably not. Why, I mean, random search is still quite stupid, right? What, and sometimes it works quite well for tuning. Which properties of a search space would we probably need so that random search performs quite well? How should your landscape roughly look like? Yeah.
Low dimensionality.
Yeah, the paper they argue because of this property here that it can also work in higher dimensions. Yeah, but look, I'm agreeing with you. You need effective lower dimensionality. Yeah, then it works. Then it maybe works. Can also work very badly in low dimensions if not something else is given. Yes?
Is the area around the moon?
Yeah, or you need, I would phrase it a bit differently, you need like a large area that you're hitting with high probability of roughly okayish solutions, right? And that is, I would say, something that we usually have in ML, because if we configure our ML algorithm, it's not going to compute complete garbage usually, right? So what you can't really have is smaller, very peaked areas where you kind of need local information to walk to guide the optimizer towards that peak, right? If you need to exploit lots of local information, really learn where the interesting areas are in the search space, then this will fail, yeah, especially in higher dimensions. And sometimes that does happen for our problems too, and I guess in the end, being more efficient is always nice. So yeah, there are of course other traditional black box algorithms. We've talked about a few already, or at least mentioned them. There's also stuff like Nailed-Meet and so on, super old. Things like simulated annealing, iterated local search, evolutionary algorithms, and so on. These are more iterative. They try to really learn where the interesting areas in the search space are, but usually none of them work very well in tightly restricted budgets. Yeah? So usually these things are made to get you a very precise solution, yeah? But they can really require thousands and I don't know, hundreds of thousands of variations. Yeah, but and they're kind of constructed in a way that they converge to the optimal. I don't know. Here's a little example. Where you can, I took a simple mathematical test function here. And you can see things like random search running here. You can see very popular evolutionary strategy here, CMAES and Bayesian optimization. I ran this for a few number of evaluations, and you can see that on these constrained budgets, BO is usually a better choice. I don't know. After 10,000 evaluations, it might not be so clear anymore. And also then, there's a certain overhead connected with BO. But I guess before we discuss that, let's actually figure out how the algorithm works itself. So our setting is now changing a little bit. So I'm not going to focus anymore on hyperparameter optimization. I'm just saying there's some black box function I want to optimize. That doesn't matter. This can be my resampled performance estimate, but it's just any black box function. And this is actually a nice thing, because if you learn Bayesian optimization, you can do way more with it than just doing AutoML. Actually, this was way more popular in other areas of science, especially in engineering, yeah, where people had to configure very expensive computer simulators, yeah, of physical processes or engineering processes. Sometimes this took days. So I don't know, one example I usually bring up here is, so a colleague of mine was doing car crash simulations. Yeah? So they had to configure settings of a car, and they were, of course, running this on the computer because that's, I mean, cheaper in terms of not destroying the car every time you want to test out the configuration. It's way more flexible, but the simulation should be accurate. And it was also quite complicated, right? So one simulator run, so for one evaluation, took, I think, between 24 and 48 hours. And they had about, I don't know, 10 to 20 parameters they needed to optimize over. And that was actually multi-crit optimization problem. Marius mentioned that it's usually multi-crit in applications. And yeah, they were running Bayesian optimization for that. And there's a lot of literature actually coming from that field, from this surrogate modeling in engineering. This is actually where I started learning this stuff. So our setup is we have some objective function S now. We can only evaluate that for inputs. We can observe the output. And for now, I want to assume, I mean, things are complicated enough. I will assume now that my input space is just real values. Yeah? And I will assume that stuff is noise-free. And the fundamental idea is, if we have some data available to us, some xi, yi pairs, and this, of course, is sampled from our objective function. Would be a nice idea if we could use that maybe to approximate f, because we want to squeeze out the last bit of information from that, right? Because if data is so costly to obtain, and we will only have a very restricted budget, might be a good idea to learn as much as we can about f, right? And now this sounds a little like regression, right? Sounds like nonlinear regression, and if we know machine learning, we already maybe know how to do this, right? So we just approximate f with a model. And the basic procedure of Bayesian optimization pretty much fits on one slide, and I guess you can implement that, the simple version, the vanilla version of that in an afternoon. Is you create something that's called an initial design. So here again, terminology becomes confusing maybe. So these points, you might call them your hyperparameter configurations. They're called design points. Yeah. And the initial design is you just place some points somehow uniformly, randomly into the input space, and you collect data because you need a starting point. And now on this data, you fit a surrogate model. So surrogate model, again, terminology, surrogate means you're replacing your true objective with a surrogate model. Yeah? It's a surrogate for the objective. You can also say it's an approximation. And this surrogate model is then used, it's in a certain sense created for, operated on, to produce a new point. Yeah? Call that a point proposal. We'll see how this works in a few minutes. This point is then evaluated. We add that evaluation to the archive. We adjust our model. So if you want to keep things simple, you just retrain. Data is maybe quite small anyhow, so maybe you don't care too much about efficiency here. You can also do some form of online updates, yeah, but I guess in many implementations we also train from scratch. And after some number of evaluations, we just return the best configuration we have seen so far. So I want to go through all of these stages now, and add in more details. So how do we do the initial design? Actually, I don't want to do this for too many minutes because this is, I would say, the least important part of it. So usually this type of design doesn't have the largest effect. Yeah? So every experiment that I have done, there's not a big difference between the things, and even the fancier ones are usually not that much better, sometimes even worse. What's more important is actually the size. And this is usually where, I don't know, literature and tutorials don't really give you too much, at least interesting theory. There's maybe some rule of thumb. Use something like 4 times D up to 10 times D. Usually the problems are, if you look into the more mathematical papers, the rules of thumb are usually too expensive. Yeah, so 10 times D is often already pushing it. Yeah, because everything in the initial design is not used for sequential learning, right? So you're basically doing some form of random search on your space, the non-iterative stuff. Here is how this is usually constructed. So you can do some form of a maximin Latin hypercube design. That sounds very complicated and fancy. It is not. So what you do is you partition your space into regular bins, okay? And then a Latin hypercube design places points into these bins so that in each row and column, yeah, and I guess you can imagine how this works also for 3D or KD spaces. Yeah, you have these, I don't know, hyper rectangles, so to speak, and in each row and column there's exactly only one active cell, and this makes your marginal distributions super uniform. Yeah, so they are I'm not even sure how to properly say that. I mean, of course, for random search you also have here uniform distributions, but here it's pretty much exact. Yeah, I don't know, super uniform. So that's like Latin hypercube designs, and yeah, there are many different Latin hypercube designs to produce for a certain space, and usually people add in one extra criterion to make them a little bit better, and this is maximum sampling, and that simply says over the space of all of my Latin hypercube designs, I want to maximize the minimum distance between 2 points. Okay, so you look at your design, you compute the minimum distance between any pair of points, and this should be as large as possible. You can also see this like as, I don't know, as ball packing, so to speak, and this ensures that the space around each design point is as large as possible. So the idea is don't run the same experiment twice, or something that's very similar. To make also the distribution of the points in the space as uniform as possible. There are other things like Sobol sampling. You can also just randomly place points into the space. To be completely honest, just random sampling is usually not so bad. This is usually what is, I don't know, advertised in the literature, and then people fight over whether Sobol sampling is better and so on. Experiments that I have done, usually random sampling was pretty good, and there are even theoretical arguments why this is maybe a good idea combined with things like Gaussian processes. Let's talk about more interesting stuff. So how does surrogate modeling work? How does acquisition function optimization work? So I will use a very stupid and simple example here, so just because I need to draw things. So I want to minimize this black box here. So that's my function that I want to optimize. It's 1D, so I can plot it. I will fit a regression model to data, so currently we don't care what that is. Might be some form for Gaussian process. Should likely be nonlinear, right? Usually our objective functions can't, I mean, it's debatable how complex they actually really are, but they're very often not like linear or quadratic. I mean, linear wouldn't make no sense anyhow, right? Because then I guess the optimal value would be at the boundary. Usually it's like somewhere in between. Probably not going to be completely a very simple polynomial. And then we would optimize that thing, right? So we approximate our expensive to evaluate objective function with a surrogate. We optimize that surrogate instead. Maybe the new point is here. Also, this tells you a lot about whether you have actually changed the optimization problem, because you really have not that much. Most of the properties have actually stayed the same, right? So the search space is still as complicated as before. It's still going to be potentially a very multimodal problem, yeah, of complicated structure. It's maybe has become white box now, because you maybe have access to your machine learning model formula, to your regression model formula. That's possible. It's not always exploited. The major thing that has changed is that the function is not cheap to evaluate, right? So now you can run stuff like evolutionary algorithms and so on a potentially very complicated search space. But you can run that for thousands of evaluations, because now one evaluation is pretty much just a prediction with your ML model, right? And that's cheap. That's not going to take 24 hours. Maybe going to take a few microseconds. And then we would evaluate that point that we just proposed. And we adapt our model. And we propose a new point. We evaluate that. And again, we adapt. And we do this again. Oh, and we now have maybe converged, right? So nothing new is happening anymore. We somehow track that and monitor that and then somehow determine that we have converged and we are finished. And reality might look like that, okay? So what actually happened was that we evaluated never really in this area here, okay? So we converged to this local minimum here, but this interesting area here, we only evaluated these 2 points, and this made our model think, our regression model think, that this area is not worthwhile. And this is a very, give me 1 second, and this is a very common theme in, I guess, in optimization in general, but in black box optimization, it's pretty important. This is called the exploration versus exploitation trade-off. So we only exploited, so to speak, and we always went there where the model thought the objective function is good. So maybe I should also say this, my standard here is always to minimize, okay? So I always want to go down. It's always some form of an error, okay? And make no mistake, we might be using some fancy ML model here, but these things are not perfect, yeah? They are not magic, and they have to operate usually with very, very low sample sizes, yeah? So this is, in the beginning, we have this initial design, this was 4 times D. And you had, I don't know, a 10-dimensional space and 40 evaluations. Your model is going to be shit in this space in the beginning. Later on, probably as well. It will maybe pick up on some interesting structure of the space, but it will not be perfect.
Just to clarify, if you say we evaluate, you mean you evaluate the expensive model?
At the expensive objective.
Yeah, the objective. So.
But that's what happened here.
Yeah.
So I took my ML, this is my, yeah, okay. We only have now 1 model, so we are not doing hyperparameter optimization. We're forgetting about that. There's the black box objective, okay? And you have a regression model approximating that.
Yeah.
Good.
And then you evaluate by checking the ground truth.
Just run, I mean, for my objective function, I must have some way of running that, right? I mean, usually it's a computer program. You can also go into the real world and perform an experiment, but then you have to come back and input the result into the computer. That's, I mean, I actually know people who are doing that, but this is somewhat annoying, right? It's much better if you can run it on a machine and then you can like automatically iterate. But this is sometimes also done with real world experiments. Okay, any other questions? I'm not sure whether it's, yep, well, okay.
I didn't get like, you mentioned briefly like 4D, like is it like a secret sauce pig? You got to hold true for everything? Like
it definitely doesn't hold true for, I mean, people recommend that. So actually the recommendations were much higher in the older days. And the idea is that you don't want your model to be too degraded. Actually, there are different schools. So some people say, I want the initial design to be quite large, yeah, so the model is not degraded. And then other people say, but I want to put like as much budget as possible into the sequential phase, because there's where the learning happens, yeah, the optimization happens. So I can show you some results later on. Hopefully, I will.
Use like a secret sauce for a particular class of cost functions or something.
It's a random formula that people came up with. So what I'm nowadays usually doing is I'm do some percentage of my budget. So I don't know, 10%, 20%, 30%, something like that. And I my own experience is rather that I make the initial design a bit larger, because Bayesian optimization, at least its vanilla version, is often quite unrobust, and having the initial design too small exacerbates the problem. Yeah, and I mean the thing is, random search is not so bad in ML, right? We just agreed upon that. So if you use 70% of our budget in this iterative phase, that's usually not too bad. If your model is completely broken in the beginning, that will create other problems. So I usually try to avoid that. Yeah.
How does having a large initial sampling space compared to having a high priority for exploration in the beginning?
Your initial design is pure exploration.
Yeah, but you have the parameters in your Bayesian optimization.
So you're saying there's an interaction potentially between the two. There probably is. Yeah, there probably there very likely is. Yes. Yeah. So you can make your initial design very large, and then maybe do a bit more, be more on the exploitative side. I'm not sure whether I want to call it like that. In your BO configuration. Yeah, but how to configure BO is now a very annoying meta question. Yeah, and I'm not sure whether I have a glimpse of that at the end. We'll see whether we make it until that. Okay. So what we now want to discuss is how do we avoid this problem. Yeah, how do we ensure that we will also evaluate this here and don't prematurely converge. And I cheated you a little bit. I mentioned this before. I said we will optimize a function based on the surrogate model, but this is not necessarily the surrogate model itself. So this is what I just did. I just optimized the prediction landscape of the surrogate. Usually we don't do exactly that. So the idea is to bake something into the process to ensure the exploration of these underexplored areas. And for that, we usually use a probabilistic regression model. So we don't only get the, I will now call this posterior mean and posterior uncertainty, okay? So we will use model classes which provide both. And a very common choice is a Gaussian process. And this gives you a posterior mean and a posterior variance, posterior standard deviation. And this S of x or S squared of x expresses somehow the confidence or the certainty in the prediction. Yeah? Okay? So this is how the model encodes how certain it is in terms of its prediction. And usually the model is highly uncertain in areas where it hasn't seen any data. Now, these models that we're using here are usually local models, in order to give us nonlinear prediction surfaces. And these models, they don't work very well if they haven't seen any data. And then this uncertainty estimate will tell us that. Okay? So in the plots, I will usually show that through these, confidence bands here. Yeah. Here you can see the confidence bands are larger because we haven't evaluated any points in this region. And we can now just make use of this extra piece of information. So this y here, this would be a random variable, okay? And through our probabilistic model, we now have a posterior distribution available, which is based on which is conditional on all of the training data, on all of the archive data we have seen so far, and also conditional on the point x, where we query the model, okay? Most prominent choice is a Gaussian process. I have some formulas, formulas also, unfortunately, also some slides on this later, but for now, do you know how a GP works? Who knows this? Okay, quite a few, this is nice. So this, is a common choice, and for this posterior distribution, that's kind of a defining property of a GP, right? Every finite dimensional marginal distribution of a GP, so we can actually do this even for collections of multiple points, this will be normal distributed. For us, it's enough to now reason about a single point, and here it's the univariate Gaussian. And this can be described by a mean and by a variance. And based on this mean and variance, we will now establish the so-called acquisition function. I guess it's maybe a good idea to just start with a simple example. This is the so-called lower confidence bound. And it's called the lower confidence bound because it is the lower confidence bound. So this is our posterior mean minus some control parameter tau, which is also a magic constant, times the standard deviation at x. So maybe it's better to go to a higher setting of tau. So here you have the posterior so the black function is the underlying ground truth, so to speak. Yeah, that is unknown to us. I can plot it here, but usually in practice we don't know this. The dotted line is the posterior mean, and we now just take this thing here, yeah, the lower confidence bound, and this is used as an acquisition function, and this is optimized now instead of the posterior mean. And of course, I mean, this very obviously by construction incentivizes exploration. Yeah, so you kind of get a little bonus for your model being I mean, you get a bonus for the posterior mean thinking here's a low objective value, but you also get a bonus for the uncertainty being high, right? And through this tau, you can control this. Okay, and unfortunately, this is now a meta control parameter of BO. If you use LCB, yeah, there are maybe ways of setting that. Maybe a good idea is to decay this over time. Yeah, use more exploration at the beginning, more exploitation in the end. Now you have to talk about decaying schedules. I don't want to go into this now. Assume we use some fixed value. I don't know, 2. Yeah. Oh my God. There are some slides missing. Actually, this is maybe a very good idea because we don't have enough time. Actually, is there a board that I can use now, right? Oh my, this is now a little bit embarrassing and bad. I did touch the slides yesterday night, but I've seen them a million times.
Every 30 seconds I ask whether you can go.
I'll do this orally. I'll do this with the mouse. I'm not sure whether this is how well this is working out. So at each point here, we have a normal distribution, right? We have a Gaussian. So one thing we can also try to compute from this is we can talk about the probability of improvement. So in our archive, we will have one point which has the best performance so far, right? The minimum performance we have observed until now. Let's say this is, I don't know, 3, right? And you now have a, can I draw? Yes. Okay. I'm not sure how angry Marius is going to be. You? This is how, I mean, this is in Y space now, right? This is our outcome, okay? And we have some Fmin value observed in our archive. And we want to minimize, right? So we'd like to be left of this, right? So we can ask ourselves, what's the probability of being here? But that's just an integral, right? It's a tail probability. And because it's a normal distribution, we can easily compute that, right? And that is called PI. That's called probability of improvement. And the most common thing is actually this here. So expectation of I of x. So that would be the improvement. Okay. So that would be, we want to be small. So I guess should be this way around. Does it make sense? So this is the value from our archive. So let's say this is 10, right? That's the constant, yeah? Currently from our archive and our current iteration. And that's our random variable. So that's the normal distribution at the point x we're interested in. Okay? And this is the expected progress we make in terms of optimization. So that's the size of the That's the expected size of the forward step. So if this is 3, this means in expectation at that point, we will make 3 steps. We will minimize our objective by 3 points, by 3 units. Does that make sense? And that is what is very often used. And that's just total bullshit what I said. This is obviously wrong and stupid. And this cannot work. If you know a little bit of maths, this makes no sense. Because if this is constant, and this is a linear function, right? I mean, what is the expectation of this? This is just f min minus expectation of y of x, right? Expectation of y of x is the predictive mean, the posterior mean. That's what I optimized in the beginning, in my example, which did not work that well. That's exactly the same thing. That's equivalent. So that can't be what we are all using, because then we would all have this premature convergence in our BO version. And this is why this is actually changed. And this, so we do a plus operation here. So that's the clipping at 0. So if you are negative, so this means a potential worsening, yeah, so to speak. Then you clip that to 0. So you can never actually become worse. Although this is likely possible, right? Or it's not ruled out. I mean, it's can be left or right hand of f min. But all of this here is pretty much reduced to 0, as if this would never happen. And this pretty much means that uncertainty can only work in your favor, but uncertainty can never work against you. This is completely unrealistic, but it enforces exploration. Okay? Does that make sense? I mean, at least a bit.
Why? I didn't get the point why it doesn't work if they don't clip.
Why maths?
Okay, again, why is
You get exactly this here.
why is the expected improvement on the integral on the left? Or no?
I'm not sure I understood the question. If you this is the improvement, right? I mean, this is f min minus y of x. That is stochastically what happens in terms of a forward step in y, so to speak, right? But a forward step can also be a backward step.
What is yx?
This thing, it's the distribution of y at x, and we just agreed upon that this is a univariate Gaussian. Okay. Okay. So and you pretty much what you are just measuring against f min now, right? So if you are here, this might be 1. It's a forward step of 1, but this would be minus 1. You're pretending that this doesn't happen. So you clip this to 0, and then you compute the expectation over this, okay? So what you do is you compute the expected value over this tail. You don't compute the probability, you compute the expected value. Okay? But otherwise you would just be mathematically completely equivalent to posterior mean optimization. Maybe a few words on surrogate models. So what do we actually need here in terms of a surrogate model? I mean, usually this is a regression model. Yeah, there are some approaches which also work with, which kind of approach this via classification. I don't want to go into this. It should probably be a non-linear local model, because our objectives are at least somewhat complicated. Should be as accurate as possible with small sample sizes. Yeah, this is not easy to obtain. We usually need these uncertainty estimates. Otherwise, we need to construct, to somehow create other forms of exploration, incentivize exploration differently, and should be somewhat robust, should work without human intervention. We need to train or adapt this iteratively in this loop. Should probably handle mixed data types quite well, and should handle dependencies quite well. And the usual choices are either GP. I'm not going to explain these formulas. This is how you can at least construct the predictions. So based on the kernel matrix here, K. So this is a local model specified through a covariance kernel function. So some of you raised your hands and you said you know this. So how are these formulas actually here produced? There's actually, if you would do a one sentence explanation of where these formulas actually come from, could you give that? Because this actually, I mean, like I said, there are whole books on GP. The theory can become quite complicated, but the computations, I mean, the prediction formulas themselves are actually not too difficult, because we are early working. I mean, Gaussian processes are pretty much distributions on functions. Yeah, that sounds mathematically quite complicated, but for the prediction, this is only based on finite data. Yeah.
I mean, you condition from the data.
And the data, so it's marginal. It's a marginal distribution, right?
But you condition on the
On the training data, yeah.
jointly.
Yes. And how is that distributed? How's the marginal distribution? Let's say we have our point X and then our training data X1 to Xn.
So this is right.
They're jointly Gaussian, right? So now what we have to compute is what is the outcome at X conditioned on the other. So we have like n plus 1 random variables, yeah, and we want to compute the conditional distribution on 1. We want to compute the distribution for one random variable when we condition on all of the others. So this is pretty much, you have a multivariate Gaussian and you condition on a subset of variables. Here, L except for 1. But there's a nice little formula for that, that you usually learn in probability theory and multivariate statistics, and that's just it. Yeah? So it's given by pretty much this linear algebra here. Yeah? And if you already know that, how to condition on variables in for a multivariate Gaussian, that's pretty much the complete formula, okay? But of course, you still have to figure out how to train the Gaussian process and so on, and what these covariance kernels are, but yeah. So let me skip all of this, some pros and some cons. So usually they work quite well.
So
Yeah.
could you? So I'm not so. So I'm not a statistician. So could you give some more insight on this kernel stuff? I understand it, and it's a likelihood to boils some kind of statistic, and but how do I?
What you're pretty much doing is a covariance kernel is, I don't know, maybe you do K. Yeah. This is what the model depends on. Yeah. This is the same type of kernel you would also use in support vector machine or any kind of kernelized ML algorithm. And what this pretty much encodes is how is the outcome between this and this point, how much are the outcomes correlated? Okay? This is what this encodes. And this is usually based on the distance between the points. So the more closely the points are together, the higher the correlation. So usually all of these covariance kernel functions are based on distances. I mean, not all of them, but many, the standard ones. And this is in a certain sense a smoothness property. It says if 2 points are very close together, the output should not differ that much. And if they are very, very far away, maybe they are nearly uncorrelated because it's a local model. So if I have a point here and a point there, their outcomes shouldn't have to do too much to do with each other. Yeah, and now you have a class of different functions that you can use. Yeah, there are Gaussian kernels, Matern kernels. Yeah. Problems with GPs are, they usually scale very badly with high numbers of data points. Yeah, usually we don't have that, but cubic scaling produces at least some annoying overhead. Yeah, they usually natively can only handle numerical features. So if you want to do these mixed and categorical spaces, you have to come up with special kernels. That's possible, but that's usually tougher work. it's also, not clear what works best here. I mean, this is definitely possible, but it's not up. I mean, it has taken us some time to figure out how this works, Maybe there are other model classes which can handle this a little bit better natively. They're usually not that robust, so, numerical problems can kick in. And they are also somewhat sensitive to the choice of the kernel and other settings. So now you have to potentially do hyperparameter optimization of your GP and your hyperparameter optimizer. It's also not so great. And so all of these things are debatable. But at least these are things to consider. Another model class which is nowadays quite popular, and I guess SMAC was very much responsible for popularizing it, are random forests. So I will not explain the basic principle of this too much now. I mean, this is a tree-based ensemble, right? Does anybody not know how a random forest works? Okay, you all know this. This is great. More problematic is the uncertainty estimator. So there are different heuristics of computing the uncertainty. You need an uncertainty estimate now, right? So you can, for example, look into the terminal nodes of each regression tree and compute variances there. You can compute the variance over the ensemble. You can do jackknife type of estimators, or cheap bootstrap versions and so on, little bootstraps. It is super unclear what is best here. So there are many different variants people have tried out. And these variance estimators are also not necessarily perfect in the sense that they have this special property, right? So we really want uncertainty to kind of smoothly go down when you increase distance between points. This usually doesn't work perfectly but you have to kind of, I guess, die one death. Either you have a nice, smooth stochastic model, which is nice and spatial. You have something that's a bit more tree-based and hierarchical and can handle these mixed spaces quite well. How am I in terms of time? Do I get my first 5 minutes back? That means I have about 50 minutes. Here, I don't know. Here's a visualization how this might look like. So very often what you want to avoid are these types of very discrete structures. So you want to have like smooth uncertainty estimates like this, which feel a bit more like a Gaussian process. And this is, I would at least say, it's not trivial to achieve that with the random forest. And if these uncertainty estimates are bad, you can also get this like premature convergence or getting stuck somewhere during the optimization. For the GP, it really nicely drops out from the maths. This is a way more heuristic construction here for the random forest. Again, some pros and cons. Usually cheaper to train. Scales better the number of data points. Usually scales also very well with high dimensions. We don't necessarily usually have that, but I guess it's a good point. Can really easily, nicely handle hierarchical spaces. Mixed categorical numerical spaces because of the tree structures. It's quite robust. Somewhat suboptimal uncertainty estimates. It's not really Bayesian. It's only, I don't know whether you care about that. I actually don't. This is certainly not normally distributed, right? So if you put an expected improvement on top of that, that relies on the Gaussian assumption. That's certainly not true for a random forest. And they usually have also poor extrapolation properties. On the other hand, that's pretty much true for any local model. If you don't bake, for Bayesian processes, you can do trend estimation and so on, which gives you better extrapolation into unseen areas. But extrapolation is, let's be honest about this, is very hard. So extrapolation means getting a prediction at a point that you really have not seen too much data at all. You have pretty much moved very far away from the bulk of the data. Okay, let's skip that. I guess I will skip. Let's skip noisy. well, maybe we have 15 minutes, so I can do 5 minutes for each of this. Let's do 5 for each, not more. I want to talk a little bit about noisy evaluations. So this is usually very often disregarded if people do BO, so they tend to forget that this vanilla version is only constructed for deterministic experiments, okay? So we assume there is no noise. Also, the Gaussian process in its vanilla version is an interpolator. Yeah? So I kind of skipped that. So this is not a normal regression model. You really interpolate through your training data points. That's something that we usually don't do in ML, right? Because we always assume that there's some noise on there. And the Gaussian process can do that. Yeah? So you can use this as an interpolator or a regression model. So if data is non-noisy, use the interpolator usually. If it's noisy, use the true regression model, so to speak. Gaussian process usually, as most ML models, usually is a regression technique. Yeah, so it does not interpolate. Because you want to smooth out the noise. In reality, I would say in most applications, usually data is noisy. Your hyperparameter optimization problem is definitely noisy. This is stochastic. We just talked about it. So we should probably not use an interpolator, but a smoother. Okay, but most ML models, most regression models are constructed like this anyhow, right? It's more like a special case that the Gaussian process can also interpolate, I guess. I guess depends a bit on your background and what models you're used to. The other problem is the acquisition function. The acquisition function also assumes that data is non-noisy. And most of the theory only goes through, and there are also some proofs for BO, especially with expected improvement. You can prove that in the long run you get something like global convergence properties and so on. These are very nice theoretical guarantees with heavy emphasis on in the long run, where we never are because we only have a few hundred or thousand evaluations. But in any case, all of this theory, I mean, the fundamental theory is also constructed for the deterministic case. So if you want to talk about noisy, I guess you have to consider the scenario, and then you also have to change the acquisition function and adapt that to the noisy case. And this is a bit harder, as it turns out. So here's how you can change the GP. So you pretty much add some. You pretty much add a term to the covariance matrix, to the diagonal, before you invert. I guess if you have seen GPs, you know this, and if you don't, you don't.
Is there a way to incorporate like dependencies between hyperparameters in the covariance matrix of the noise?
Can you be a little bit more specific about this?
Like, I mean, as you said, my acquisition function might be noisy. So in a hyperparameter A and B that depend on each other, because the space is very likely non-Euclidean. So
but this is kind of automatically done with the GP anyhow.
So it's totally like it's not a problem to assume that my noise covariance matrix is diagonal.
No. And I mean, GPs are very flexible for this. I mean, they are kind of the problem is that people have become very good. I mean, there are people who can adapt GPs very nicely to tasks at hand. The problem for us is that we need to run this fully automatically, right? So we can't really reason about, hey, what covariance function here is nice, which specific form, right? We can't exactly write down, I don't know, a certain noise structure and so on. This is what people usually do when they are like data scientists using GPs. But it's definitely possible. The question is how to automate that in a robust sense. Okay, here is one version, for example, to do an acquisition function for noisy stuff. And as you can see, this already begins to look a little bit more complicated, okay? So let me walk you through this at least a bit. So here you have the expected improvement formula. So this is exactly the thing that we just discussed, okay? And this now adds in a penalty term. No, actually it already changes the expected improvement formula. So we have this F min value, right? So this is the value we compare against when we do the integration here, right? That's the best value from the archive, the best Y value, the best outcome from the archive. But this is now noisy as well, right? So I said before that's a constant because we observed it in the deterministic case. Now it's also random. So here, this is sometimes called the plug-in value for some weird reason. So a simple choice is just to smooth this out with your regression model. Yeah? So you don't take the observed value, but you form a prediction with your surrogate on that. And then you use, I don't know, F min hat, so to speak. Okay? That's, I guess, fairly simple to explain. And then you also have a penalty term here to kind of re-weight your expected improvement. So you can just only do this, and this sometimes also works well, just using expected improvement with plugin. But yeah, this is what is called the augmented expected improvement by 1. This is now also about 20 years old. So here they did this penalty, and I don't want to explain every, I don't know, component of this formula, but the idea is, so this uses the local uncertainty estimate, but this also uses here this estimated nugget effect. Yeah, that was the thing we put into the regression model of the GP. And this accounts for the diminishing returns of additional replicates when the predictions become more accurate. So the idea is if you have already evaluated quite often in a certain area, then additional replicates usually don't gain you too much anymore. So this, in a certain sense, it penalizes that. If you set this here to 0, then you pretty much get the normal expected improvement with plugin, which is also, I don't know, a simple, plausible version to do for noisy optimization. But I guess at least you want to smooth out the Y into the F min to the F min hat. Here's another technique. I mean, there's lots of, I don't know, research out on this. Here's a very simple technique. I quite like that because it's extremely simple to explain. There's not too much theory, I guess, out there. Very often papers I don't see this, but in experiments this usually works quite well, and it's also simple to explain and implement. And this is called reinterpolation. And this works in the following manner. So you now fit 2 GPs. So the first one is a regression GP. Okay, that's simple. We know how to do this. And then we use this regression model to smooth out all of our Ys. So not the plugin, not just the F min, the best value, but we just have the model predict on the complete archive. So we get a smooth version without the noise, assuming that the model would be correct, which is, it's not, that is an approximation. And then on this smoothed out data, we now fit an interpolating GP, and then we just run normal Bayesian optimization with normal expected improvement and kind of keep our fingers crossed and hope for the best. And this actually does work quite well in empirical results. It's really simple to implement. The only thing you might not want to complain about is that you have to fit 2 GPs, so it's twice as expensive in terms of overhead. Even that's not true, because the major component that's expensive for the Gaussian process is like learning its hyperparameters, which are in a certain sense the parameters. So these are the settings of the covariance function, and you can do this in a Bayesian manner. And this is where most of the time is spent in GP training. Learning the so-called length parameters of the covariance kernel. The thing is, if you do this on nearly the same data, it's just a smoothed out version, then you can just kind of copy over the results from the first stage, or at least use this as a warm start, and you can make this a lot cheaper. So this is not a factor of 2, but usually way less in terms of overhead.
Why, how with the Elton? Like, why can't I just use the uncertainty of the regression model? Why do I need manipulating?
It's not about the uncertainty. It's about the uncertainty estimate is okay. It's because of because of the construction of the acquisition function, this assumes that you want to use standard EI. That's the point. But standard EI is constructed for an interpolator. Okay? That's a bit harder to explain. If you give me an additional hour, I could do this, but yeah, I guess not now, and not if. I guess then Eva, Katharina, or Marius will become very angry. I'm even a little bit too slow now. Okay, maybe I'll skip the empirical results. I'll wrap up a little bit. Actually, I'll just do some words on parallel Bayesian optimization, if that's fine with you. I guess that's very relevant for practice. So until now, we have only talked about sequential stuff, right? So we produced one point, we validated that, and then we adapted our model. But we're running computer experiments. And these computer experiments are super expensive. That was the complete assumption of our setup. But usually we have more than one core and more than one machine available to us, right? So why don't we produce 10, 20, or 50 points in parallel to evaluate? And this is parallel Bayesian optimization. This is certainly not trivial. The whole algorithm is really constructed in a very sequential manner. That was the idea, to like squeeze out as much as we can from each sequential step. It is not, I mean, it's possible to produce a batch parallel version where you have multiple points being proposed. Now, written papers on this myself, but this is not simple. It's not completely clear how to do this. I guess there's one clear mathematical way how to do it, but this is also very expensive. Again, and there's another problem associated with this, and that is that this is usually constructed in a batch parallel manner. And with that, I mean, I have my current GP model, and now I produce 20 points. That's usually, I mean, it's unclear how to do this best, but let's assume we can do this somehow. Now we evaluate these points, and now we wait until all points have been evaluated, and then we adapt the model with the 20 new points. And that would work out very nicely if all of these points take the same time to evaluate. And of course, as a mathematician, we just assume that. And in practice, this is very untrue. And this is especially very untrue in HPO, right? So look at these, remember again, these pipeline graphs, right? So you have different algorithmic components that you trigger. Some of them will take way longer than others. But now you have to wait for the slowest component. So this is sometimes called, I don't know, synchronous parallelization, and this is usually not so great. There's a very simple asynchronous decentralized version, and I think this is even, I'm not sure whether you want to implement this yourself, but yeah. We had many of these synchronous parallel things in our software for many years. Since 1 or 2 years, we implemented this asynchronous stuff. This was actually not so hard, and I think I pretty much now exclusively use this. And it's also not so hard to explain. So the idea is you have some central storage to share and exchange information. And this is where your archive is. And now you have K nodes where your workers run. And the workers are pretty much vanilla BO processes. So when they have some time, they query the archive, they take in the training data, and now they run Bayesian optimization and produce one point. And then if that point is being proposed, they evaluate it on their own node, on their own machine, and then they write the result back. And this can work nicely. And they just kind of, I don't want to say they run independently, they share the same training data, and through the archive they communicate. Now this is pretty much how asynchronous decentralized Bayesian optimization works. So you run K of these BO algorithms with a shared archive. There's exactly one problem associated with this. Can you? Yeah, you were fastest.
The optimizers might all look in the same space.
Exactly. And do you also have an idea how to repair this? So the thing is, you propose a point. The point proposal usually it takes, I don't know, a few, seconds maybe. but usually you don't have to wait too long for this, right? The problematic thing is the evaluation, right?
So you might give a higher weighting to points that are away from the last proposed point.
Yes, and in a certain sense, this is exactly what happens. And there's a very simple trick how to do this. This is sometimes called, I don't know, constant liar or the liar principle. It means you fake a y value. Somewhere between the best observed f min and the worst observed f max. Yeah, somewhere in between. But the thing is, just by faking a value itself, the uncertainty in the GP goes down, right? And the worse you make that point, the more the posterior mean also goes up, which is bad. Okay? So until you have obtained the true evaluation, you put in this fake label, and this means that all of the other BO processes will very likely not produce a point near this region. Posterior mean would have to be drastically good in this area in order for this to happen, but then you maybe want more points. Yeah? And that's pretty much it. Yeah.
If you end up computing, wouldn't it make more sense to sample for the actual GP, the fake y values, and then average the metric over multiple samples?
You can just do posterior sampling and do exactly that. That's also a very common procedure. Yeah. So usually you can sample somewhere between f min and f max, or you just sample from the thing itself. But usually it's a somewhat unclear trade-off, right? How much, to penalize currently evaluated areas. This is pretty much again the exploitation trade-off, which is quite unclear. Yeah. I'm now 7 minutes over time. I don't have too many slides left. These were I'm not 7 minutes over time. These were exactly the 10 minutes that were stolen from me in the beginning, or that I guess I would end here. I have some slide there. I'll skip Hibo. Look into Hibo. It's very interesting. We're currently running. Many of us, I guess, have over the years run large-scale meta benchmarks for Bayesian optimization. Not all of them have been published. There's a lot of, hidden knowledge about what works and what does not. Maybe 2 or 3 final sentences. First of all, these experiments are very expensive. Yeah? These experiments are extremely noisy. This is usually a problem. So if I do this on small sample sizes, I mainly only observe variance. Yeah? So nowadays we run on hundreds of different, hopefully realistic BO problems. There are many of us here from the organizer teams have also produced benchmark suits to get our hands on that. That's also a huge amount of work. Yeah? If there's one thing that I see from all of the experiments that usually gives you lots of performance gain, it's not using expected improvement instead of, LCB or whatever, or maybe even posterior mean, or using, the perfect uncertainty handling mechanism in random forests. By far the first, meta configuration that gives you the largest performance boost is optimizing on log scale. A little bit weird, right? And I guess we have observed this somehow consistently. And this is interesting because it's in modern toolboxes, it's nowadays usually enabled. But if people run their own BO, they usually don't do this. I've also seen, and I guess that was your question about interactions between these settings. Yeah, this is also unfortunately true as well. Yeah, sometimes they're very non-trivial interdependencies, and this makes it very hard to, give clear recommendations what to do. Yeah. So if people, change the one setting but not the other. Yeah.
Do you mean log scale for the inputs or for the targets?
And for the targets. So I skipped a little bit details on Hibo. So Hibo is a modern implementation of Bayesian optimization that has quite strong performance. Hibo actually does input transformations and output transformations. Not too complicated ones, I have to say. And the ones that are a little bit more fancy also don't seem to be too worthwhile. So I'm not too sure how much. Do you have results on the input warping, whether this really helps? I mean, there's like pretty much you bring everything on X into on the same scale, so to speak. Yeah.
It's not for random forest.
For random forest, this cannot make a difference, right? Mathematically not. But and for GPs, you didn't look at this too much, right? Yeah. I mean, for GPs, usually a simple transformation on I don't know, on a 0-1 hypercube is good enough. Most of the software that I have used has done this for decades by default. The log scale seems to be quite important. For more fancier exotic transformations, I don't know, ask me again in 1 month or so. Yeah. Currently our cluster is also not working, so I wanted to have more results for today. Yeah. Yes?
There was a method that was used for the surrogate. It wasn't for hyperparameter optimization, it was for something else. But they were using in Gaussian processes something called expected information gain, which, if I remember correctly, was the expected reduction in entropy at one point.
Yes. There are many more complicated variants for acquisition function construction. Yeah. Entropy search, expected information gain is one of these. Yeah. These are usually harder to explain.
I've seen in optimization libraries that often the default behavior is to switch to 3 different acquisition functions.
This is also done in Hebrew, or they handle this in a multi-criteria fashion. So like internally, so to speak. Expected improvement usually gives you, I don't know, the strongest theory, so to speak, but this doesn't necessarily translate so that this is perfect in practice. The thing is that I guess I would phrase it like that. So they all have different. It's pretty much mathematically nicely describable that they all compute different trade-offs on the exploration front, and it's unclear where you want to be there. So Hebrew and other implementations just say, okay, we try out different ones. This can also be a nice handle to use your budget in parallelization. You try out different exploration-exploitation trade-offs. Yeah, for example, you use your LCB and you just vary the tau. Yeah, and you run this on different workers. Frank wrote many years ago a paper on that. And then this was called QLCB. And this also sometimes works quite well.
Is there, like, let's say I want to get the hyperparameter configuration for my neural network, and one hyperparameter is the width. Like the width of the network. But that's the width.
We don't care, right?
It doesn't matter.
Doesn't matter. Okay.
It doesn't matter. The point is that the network and evaluation get forward plus. So is there, like, do people take this into account?
Yes.
Okay.
Yeah. These are all questions, I don't know, for a BO session number 2 or 3, which I guess we currently don't have. Are people talking about more advanced Bayesian optimization things here during this week? Yes. You can do this. You can do something like expected improvement per second. This is something that's very old. Many of you have seen the SNUG paper on Bayesian optimization. Do you know this? Practical Bayesian optimization by SNUG. Has anybody heard of this? Okay. Interestingly, this is very often cited as like a fundamental reference for Bayesian optimization. I guess one of the major new ingredients it brought to the table was this expected improvement per second. So you kind of have a second surrogate model that now estimates time. And you have no preference to evaluate configurations which are fast to evaluate but bring you a big improvement in performance. On the other hand, this is in practice not very often used, although I would say that this is highly relevant for HPO as well, again, because there are these heterogeneous runtimes, right? which are interesting or problematic in parallelization, but they are already also interesting in the sequential optimization, as you just pointed out, right? So you don't want to evaluate something that is, runs for a very long time and then is also bad, right? That's kind of the horror combination. And sometimes there are configurations where the model does not even terminate, because it becomes, you could use, like, I don't know, a deep neural network with 50 million layers, so to speak. And maybe this is even a bad choice. And then you waste lots of hours just trying this out, although you could have known this before from your archive data. I will stop now.